Right now, at this exact second, somewhere above your head and mine, a machine older than the internet, older than cell phones, older than most of the people reading this, is drifting through a region of the universe that human beings were never meant to touch. It is moving at roughly 38,000 miles per hour. It is so far from home that the light from your phone screen would take almost a full day to catch up with it. And in the last few months, NASA scientists poring over its data have confirmed something that has quietly unsettled the space science community. Something out there in the black gap between our sun's protection and the rest of the galaxy is not behaving the way any model predicted. It is hotter than it should be. It is denser than it should be. It is louder in a way that should not exist at all in the vacuum of space. And the machine reporting all of this back to us is dying, slowly, deliberately, one instrument at a time, racing against its own, failing power supply to send us as much of this data as it can before the silence comes. This is the story of Voyager's newest and strangest discovery, why NASA is calling parts of it genuinely alarming, and why what these two aging spacecraft are finding out past the edge of our solar system might be one of the most important and most overlooked stories in the history of space exploration. To understand why this new discovery matters so much, you have to go back to the beginning, because nothing about this mission was supposed to happen this way. In the late summer of 1977, NASA launched two nearly identical spacecraft within weeks of each other. The reason had nothing to do with ambition and everything to do with timing. The outer planets of our solar system had drifted into an extremely rare alignment, a geometric coincidence that occurs roughly once every 175 years. And that alignment made it possible for a spacecraft to slingshot from one planet to the next using nothing but gravity. Jupiter to Saturn to Uranus to Neptune, a grand tour of the outer solar system in a single mission, something that would otherwise take decades to accomplish with separate launches. NASA had a 5-year window to catch that alignment. They caught it. The spacecraft themselves, Voyager 1 and Voyager 2, were engineered with an expected working life of about 5 years. Nobody involved in building them seriously believed they would still be operational, let alone still making discoveries half a century later. Voyager 1 finished its planetary flybys in 1980. Voyager 2 wrapped up its own tour in 1989, capping it off with the only close encounter any spacecraft has ever made with Neptune, a flyby so distant and difficult that it remains, to this day, humanity's single detailed look at that ice giant. After that, both probes were pointed away from every planet, away from the sun, out into open darkness, and told, essentially, to keep going and keep talking for as long as they possibly could. They have never stopped. Decade after decade, generation after generation of engineers at NASA's Jet Propulsion Laboratory have sat in the same building, listening to a whisper of a signal crossing, billions of miles of empty space, carrying information from machines that, by any reasonable engineering standard, should have gone silent decades ago. Voyager 1 is currently more than 15 billion miles from Earth. Voyager 2 trails behind it at just over 12 billion miles. These numbers are so enormous that the human brain cannot really process them as distance in any intuitive way, so it helps to think about it in terms of time. Instead, sunlight takes about 8 minutes to reach Earth. A radio signal from Voyager 1, traveling at that same speed, the fastest speed in the universe, takes nearly a full day to arrive. By the final months of 2026, Voyager 1 will cross the threshold of being one full light day away from Earth, the first human-made object in history to do so. If something goes wrong with a spacecraft at that distance, engineers do not find out for almost 24 hours, and if they send a command to fix it, they wait almost another full day just to learn whether that command worked. There is no other machine, no other human creation, operating under conditions anything like this. That isolation is part of what makes the current crisis so tense. Both Voyager probes are powered by something called a radioisotope thermoelectric generator, a device that produces electricity from the heat given off by decaying plutonium. There are no moving parts, no solar panels, nothing that can be repaired or replaced from Earth. It is simple, elegant engineering, and it has kept both spacecraft alive for far longer than anyone expected. But it comes with an unavoidable expiration date, the plutonium. And inside those generators has a half-life of roughly 88 years, and it has been decaying, steadily and without mercy, since before either spacecraft ever left the ground. As of this year, Voyager 1's power output has fallen to less than half of what it produced at launch. The decline is not sudden or dramatic. It is worse than that. It is slow, steady, and completely unstoppable, bleeding away at a rate of roughly 4 watts every year. 4 watts sounds almost meaningless in a world where a single household appliance uses more power than that. But on a spacecraft where every function, every heater, every instrument, every radio transmitter is fighting over a power budget barely larger than what you would need to run a dim light bulb, 4 watts a year is the difference between a working mission and a dead one. To manage that decline, NASA engineers have spent years doing something close to medical triage, deciding which systems live and which systems get sacrificed to keep the rest of the spacecraft alive. Heaters have been shut off, leaving instruments to operate in conditions colder than they were ever designed for, and somehow they kept working anyway. Cameras were switched off years ago, since there was nothing left to photograph in the featureless dark beyond the planets. Instrument after instrument has been quietly and deliberately killed, not because it broke, but because keeping it running would have meant losing something else that mattered more. Earlier this year, engineers made one of the hardest of these calls yet, deactivating an instrument that had been running almost continuously since 1977, nearly half a century without a single day of rest. It had been measuring charged particles and cosmic rays, mapping the invisible pressure changes in the region beyond the sun's influence. Losing it was a real scientific loss. But just weeks before that decision, Voyager 1 had experienced an unexpected and unexplained power drop during a routine maneuver, a drop that nearly triggered the spacecraft's automatic fault protection system, an emergency mode that shuts down critical functions and forces a slow, risky multi-day recovery process at a distance where every single step in that recovery takes almost 24 hours just to confirm. Engineers had to choose. They chose to sacrifice the instrument rather than risk losing the whole spacecraft. That sacrifice bought time for something NASA engineers have started referring to almost like gallows humor as a last-ditch power reshuffling maneuver, a complete and unprecedented reorganization of how each spacecraft distributes its dwindling electricity. The plan involves switching off several systems simultaneously and rerouting power through lower consumption alternatives, essentially trying to squeeze a few more years of scientific life out of hardware that was never designed to be adjusted this way, using software that cannot be updated on a machine so old that many of the engineers who built it have since passed away. It is being tested first on Voyager 2, since it has slightly more power in reserve and is somewhat closer to Earth, making it the safer of the two to experiment on. If those tests succeed, the same maneuver will be attempted on the more fragile Voyager 1 later this year. There is no guarantee it will work. Every single command sent to either spacecraft is, at this point, a genuine gamble because there is no room left for error and almost no way to react quickly if something goes wrong. And yet, in the middle of all this decline, all this quiet and reluctant sacrifice, both spacecraft are still finding things. Not small things, not footnotes. They are finding evidence that the region of space just outside our solar system, the zone scientists call interstellar space, is fundamentally different from what every model predicted it would be. And some of what they have found is the part NASA scientists are now calling, quite openly, unsettling. Start with the boundary itself, the place where our sun's influence finally gives out and true interstellar space begins. For decades, nobody knew exactly where that boundary was. Early guesses placed it somewhere near Jupiter's orbit. As Voyager kept flying and kept not finding it, those guesses kept getting pushed farther and farther out. Eventually, both spacecraft did cross it, Voyager 1 in 2012 and Voyager 2 6 years. Later in 2018, and what they measured there was not what anyone expected. As each spacecraft passed through this boundary, their instruments recorded plasma temperatures between 30,000 and 50,000 degrees Kelvin, a wall of superheated particles sitting at the very edge of our solar system. Scorching hot by any normal definition and completely unpredicted by the models scientists had built. Beforehand, nobody had placed a thermal wall that intense into their calculations. It should not have been there. It was there anyway. Both spacecraft measured it independently, years apart, in different directions, and got the same terrifying result. A wall of heat sitting at the border of everything we call home, and to this day, scientists do not fully understand why it exists. Then there's the radiation. Inside the bubble our sun creates around the solar system, its magnetic field acts as a kind of partial shield, deflecting a significant portion of the high-energy particles that constantly stream in from across the galaxy. The moment Voyager 1 crossed that boundary in 2012, its radiation instruments recorded a sudden, dramatic surge in high-energy particles slamming into the spacecraft. A surge that happened almost instantly as it left the protection of the heliosphere behind. That part was expected. What was not expected was just how intense that radiation environment turned out to be. Out there, past the edge of our solar system, Voyager is being continuously struck by particles that have been traveling through the galaxy for millions of years. Cosmic radiation far more intense than anything in direct measurements from inside the solar system had prepared scientists for. The spacecraft was built to withstand radiation, and it has survived nearly 50 years of exposure. But the environment it is now sitting in is measurably harsher, more energetic, more hostile than anyone calculated. Our sun has been quietly shielding every living thing on Earth from the true intensity of that radiation for our entire existence, and we only fully understood the scale of that protection once a machine finally stepped outside of it and reported back what it found. The density readings are, in some ways, even stranger. When Voyager 2 crossed into interstellar space, scientists discovered the plasma density on the other side of the boundary was running at roughly double what their models had predicted. And it has not stayed constant. As Voyager 1 has continued pushing deeper into interstellar space, the density of particles surrounding the spacecraft has been steadily climbing year after year. Within a span of just a couple of years, electron density measurements around the spacecraft showed an increase of roughly 40 times over the baseline level recorded just outside the solar boundary. 40 times denser, and not gradually, but sharply, as if the spacecraft had driven directly into some kind of cosmic traffic jam. Scientists have proposed a couple of competing explanations. One theory suggests that particles from interstellar space slow down as they approach the edge of our solar system, backing up like cars at a bottleneck, and that Voyager is now driving straight through that pileup. Another theory suggests that the interstellar magnetic field compressing against the edge of our solar bubble is physically pushing charged particles away from the boundary itself and concentrating them farther out, exactly where Voyager now finds itself. Nobody knows for certain which explanation is correct yet. What is certain is that the region beyond our solar system is getting more crowded, more turbulent, and more unpredictable the farther Voyager travels into it, and that fact alone is forcing scientists to rewrite what they thought they understood about the space between the stars. And then there is the sound, or more precisely, something that functions like sound in a place where no human ear could ever survive to hear it. Interstellar space is not a true vacuum. It is filled with extremely thin, extremely cold plasma, ionized gas that can carry pressure waves in much the same way that air carries sound on Earth, just at densities and frequencies almost too faint to imagine. Voyager 1 carries a plasma wave instrument, essentially a pair of long antennas trailing behind the spacecraft, sensitive enough to detect these waves. For years, that instrument had only picked up brief, sharp bursts of activity, triggered whenever the sun released a powerful eruption strong enough to send a shock wave rippling all the way out to Voyager's position. Useful data, but only occasional, arriving in short flashes whenever the sun happened to cooperate. Then scientists identified something else buried in that data, a continuous, persistent hum resonating steadily in the emptiness of interstellar space, unrelated to solar activity, simply present, all the time, everywhere the spacecraft traveled. Researchers involved in identifying the signal described it as something close to a single steady musical note, sustained continuously, shifting only very slightly over time. Not a malfunction, not background noise. A genuine ongoing vibration of the plasma filling interstellar space itself, allowing scientists, for the first time, to measure the density of that region continuously rather than waiting for the sun to send an occasional signal their way. It changed how astronomers can study this part of the universe entirely, turning an occasional flash of information into a steady stream of it. Layered on top of all of this is the magnetic field data. The interstellar magnetic field, the extremely faint but very real magnetic presence permeating the space between stars, was measured as tens of thousands of times weaker than Earth's own magnetic field, and yet it turned out to be stronger than scientists had predicted it would be. That extra, unexpected strength turns out to explain something that had puzzled researchers for years. Our sun cycles through roughly 11 years of rising and falling activity, and scientists had assumed that during periods of high solar activity, with more solar wind pushing outward, the protective bubble around our solar system would physically expand, and that during quieter periods it would shrink back. When Voyager 1 crossed the boundary in 2012 and Voyager 2 crossed it 6 years later, during a period of comparatively high solar activity, scientists expected to measure a noticeably larger bubble than before. They did not find one. Both spacecraft recorded the boundary sitting at almost exactly the same distance, essentially unchanged. The explanation, once researchers worked through the data, came down to that stronger than expected. Interstellar magnetic field pushing back against our sun's bubble with more force than anyone had accounted for, holding it in a kind of steady equilibrium regardless of what our own star was doing. Our entire solar system is being squeezed from the outside by forces that turned out to be considerably stronger than anyone had calculated. And we would have no way of knowing that if these two aging machines had not physically been there to measure it. All of this is being recorded by spacecraft that, by any rational engineering standard, should not still exist. Voyager 1 currently has only a small handful of active science instruments remaining, most of its original suite of 10 instruments long since shut down to conserve power. Voyager 2 has only a few more than that. What remains running are, almost by accident of fate, exactly the instruments best suited to studying the plasma waves and magnetic fields of interstellar space, the two things that turn out to matter most for understanding this newly discovered environment. It is almost as if the mission somehow knew, decades in advance, which tools it would need at the very end, kept them alive through years of shutdowns and power cuts, and is now using them at precisely the moment they are needed most, to answer questions that did not even exist when either spacecraft left Earth in 1977. It is also worth remembering that the boundary itself, this thermal wall, this dense turbulent zone, this hum, is not a smooth, uniform shell wrapped evenly around our solar system. Voyager 1 and Voyager 2 crossed it at different points, years apart, traveling in completely different directions through the sky, and what each spacecraft measured at its crossing point was noticeably different from the other. Voyager 1 recorded intense fluctuations in the magnetic field at the exact moment it crossed the boundary. Voyager 2 did not detect that same turbulence, but instead found a thin layer of unusually hot plasma sitting just outside the boundary that Voyager 1 had missed entirely on its own crossing. The edge of our solar system, in other words, is not a clean, symmetrical bubble at all. It is a chaotic, unevenly shaped structure, compressed on one side, stretched on the other, actively being pushed and reshaped by whatever is happening in the interstellar medium surrounding it. And these are only 2 data points, gathered from only 2 directions, out of the entire 3-dimensional boundary surrounding our solar system. The vast majority of that boundary has never been measured by anything at all. There is now a newer spacecraft in the picture as well, launched in 2025, designed specifically to build on what Voyager started, mapping the shape and behavior of this boundary with a level of detail no previous mission could achieve. Its data, combined with what Voyager continues to send back from directly inside the region being studied, is producing the most complete picture ever assembled of the strange, uneven, asymmetric bubble our entire solar system exists inside of. And every new piece of that picture seems to raise more questions than it answers. Our sun is moving through the surrounding interstellar medium at tens of thousands of miles per hour, physically plowing through a region of space that is pushing back against it, and Voyager is drifting through the disturbed wake left behind by that motion, directly sampling an environment shaped by forces we are only now beginning to understand. Think about what that actually means for a moment. For nearly all of human history, everything we believed about the space beyond our sun's reach was built on inference. Astronomers pointed telescopes outward, measured faint light from distant stars and galaxies, ran the numbers through models built on assumptions about temperature, density, and magnetic behavior, and called that our best understanding of interstellar space. It was reasonable science. It was also, it turns out, wrong in several important ways, and we only found that out because 2 machines built in the 1970s happened to physically survive long enough to go there and check. That distinction matters more than it might seem at first. A model can be elegant, internally consistent, and still be describing a universe that does not actually exist outside our own front door. Voyager did not confirm the models. It broke them, one measurement at a time, and in doing so, it handed scientists a version of interstellar space considerably more violent, more energetic, and more alive with activity than the quiet, empty void so many of us were taught to picture in school. Meanwhile, back on Earth, the team keeping these spacecraft alive is shrinking along with the power budget they are managing. Many of the engineers who designed the original systems on Voyager have retired or passed away in the decades since launch, taking with them a kind of institutional memory that cannot simply be looked up in a manual. The current team relies on decades-old documentation, some of it typed on machines, that no longer exist, some of it recorded only in the memories of engineers now in their 70s and 80s who worked on the project when it first launched. Every command sent to either spacecraft has to be written in an old, largely obsolete programming language, tested painstakingly against decades-old simulators here on Earth, and then transmitted across billions of miles with the full knowledge that if something goes wrong, there will be no quick fix, no patch, no do-over. It is, in a very real sense, one of the last living connections to the earliest era of deep space exploration, kept alive today by a small and aging group of specialists who understand systems that most modern engineers have never even been trained to work with. Here is what makes all of this land differently than most space stories. This is not a telescope looking at something from a comfortable distance. This is not a simulation or a model or an educated guess built from indirect evidence. 2 machines, built before most of the technology in your home existed, launched by people who assumed they would stop working within 5 years, are right now physically present inside the region of space these discoveries are describing. Every strange reading, every unexpected temperature spike, every unexplained density surge, every note of that continuous hum is coming from instruments that are actually sitting inside the phenomenon being measured. Nothing else humanity has ever built has done that. Nothing else currently planned will do it again for a very long time. The next dedicated interstellar mission, if it is ever fully funded and launched, would take at least 15 years just to reach the distance Voyager 1 has already traveled, and considerably longer to push any farther than that. Which brings us back to where this all began, to a spacecraft losing power so quickly that engineers had to deliberately kill one of its own instruments just to keep the rest of it alive a little longer, to a maneuver nicknamed for the beginning of the universe being attempted on a machine that might be nearing the end of its own operational life, to 2 aging probes racing against a ticking clock made of decaying plutonium, trying to send back as much information as possible before the silence finally comes. If the power reshuffling succeeds on both spacecraft this year, there is a real possibility both Voyagers could keep transmitting data well into the 2030s. If it fails, the mission could end within just a few years. Nobody currently working on this mission knows for certain which outcome is coming. What they do know is that the region of space these 2 machines are sitting in right now is hotter than predicted, denser than predicted, more turbulent than predicted, and filled with a continuous, physically real vibration that nobody expected to find out there at all. The universe just past the edge of our own solar system is not empty, and it is not quiet, and it is not behaving the way any model said it would. For now, and for as long as these 2 machines manage to keep talking to us, Voyager remains the only voice we have coming directly from that place, describing a reality that is stranger, and in some ways more unsettling than anything scientists had prepared for. If this story pulled you in, stay close, because Voyager's data keeps arriving, and every new signal is rewriting a little more of what we thought we understood about the space just beyond our own front door. Subscribe so you do not miss what comes back next. Share this with someone who needs to hear just how strange the edge of our solar system really is. And drop your thoughts below, because after 49 years and more than 15 billion miles, this story is still nowhere near finished.